obtaining the maximum amount of product from a reaction depends on the proper set of reaction conditions. Recall that if something's at equilibrium, that the forward rate equals the reverse rate, and there will be an exchange going on, and the concentrations or partial pressures of the different species will remain some constant, and that ratio will equal to K. However, if we add some stress to the system by adding more reactants, products, etc., changing pressure, changing temperature, things are going to affect that equilibrium, and things are going to shift one way or the other to relieve that stress until it reaches equilibrium again, and all the concentrations, be it new concentration values, will still equal that ratio of that K. Well, this gets us to something called Le Chatelier's principle. Chatelier's principle states that when a system in a chemical equilibrium is disturbed by a change of temperature, pressure, or concentration, the equilibrium will shift in a way that tends to counteract this change until equilibrium is reestablished. That's the point where that forward reaction rate equals the reverse reaction rate. Let's talk about removing and adding products, okay, or reactants to the reaction. If a chemical system at equilibrium is disturbed by adding a gaseous or aqueous species, recall that solids and liquids, okay, on that part of the equilibrium, so that part of that expression, the reaction will proceed in such a direction as to consume part of the added species. Okay, so if we add a species, it's going to shift in the direction to consume that added species. Conversely, if a gaseous or aqueous species is removed, meaning taken away by complexing it or it escapes as a gas, etc., the system will shift to restore that part of the species. Meaning if it's going to be something removed, then we're going to have to shift to produce more of that. Okay, this shift will occur until equilibrium is reestablished again. So you have a reaction, say A plus B gives me C plus D. If I was to add any A to this reaction, okay, it's now imbalanced. I have more A than I'm supposed to have at equilibrium. It's going to have to consume up that A by shifting to the right. Okay, and produce more in C to balance it out. Same thing if I add B. If this system is at equilibrium and I add B, I'm going to have to consume that B to get it, produce more C and D to get that equilibrium, so it's going to shift to the right. If I add C or D, okay, I'm at equilibrium and then I add some C. Well, I want to consume it as well and produce more A and B, so I'm going to shift to the left. In essence, what's happening here is whatever side I added on, I'm going to shift to the opposite side. We can do the same thing if we remove stuff. Okay, let's say I remove A. Say I can somehow complex A by adding something to it. Okay, or maybe it's a gas and it escapes, so I'm just letting it to the atmosphere, so it comes on out of the reaction. Well, if I remove it, I'm at equilibrium, so I have all my concentrations I need. Now I have less A than I had before. Okay, well then I'm going to have to reproduce that A to get back to equilibrium. So it's going to end up shifting toward that way that I removed the species, in this case A, so it's going to shift to the left to produce more of that A to get back to equilibrium. Same thing for B. Okay. Say I'm remove some C. Okay, once again, I'm at equilibrium. I pull some C off. I'm going to have to shift to the right, okay, to produce more C to get back to that equilibrium. So in essence, if I remove any species, I'm going to shift to that direction, okay, to produce more of that species to get back to equilibrium. So in essence, if I add anything, okay, I'm going to shift to the opposite side. If I remove a species, I'm going to shift toward that side to produce more of that species. Now, in the homework, there's going to have some questions that have A, B, C, and D, but there's a lot of them that have chemistry involved and reactions written. So you got to be able to handle the chemistry. That goes back to your general chem knowledge to be able to make decisions. Here's an example. Say I had a reaction. Instead of B, I had hydronium ion, okay, as B. And I said, now I got this reaction. It's at equilibrium, and then I added some sodium hydroxide to it. Okay, and sodium hydroxide is not one of the reactants or products in this reaction. The question is, how does adding sodium hydroxide affect that hydronium? Well, what happens with acids and bases? Okay, and they neutralize each other. So if I add sodium hydroxide, that means I'm consuming up H3O, so that's concentrations going down. Even though it's not part of the equilibrium, I'm basically consuming up that hydronium that's part of that. So if I'm removing it, I'm going to have to replace more. This reaction is going to have to go to the left to produce more hydronium to reach equilibrium again. Okay, so you got to realize as you're going through these, you got to look at the chemistry going on to decide what's happening. Similar, we will eventually talk about temperature and endothermic, exothermic. You're going to have to look at the information in the problem to decide which way it's going to go to relieve that stress. A pressure change caused by changing the volume of a reaction vessel can affect the yield of products in gaseous reactions, only if the reaction involves a change in the total moles of gas present. Let's look at this example. I got dinitrogen tetraoxide goes to nitrogen dioxide. Okay, let's say, suppose the system is compressed by pushing down on the piston. In other words, I'm decreasing the volume of the space. Which way would this reaction shift to relieve that stress? So in essence, you have a container. We have our reaction, dinitrogen tetraoxide, forming 2 nitrogen dioxides. Okay, we say we have a piston. Okay, so we said we increasing the pressure by moving that piston down. Okay, well, if I move the piston down, my volume is now decreasing. Okay, and the volume is getting less. Question is, can this shift one way or the other toward the reactants to the products and relieve that stress? In essence, what we're looking at is a decrease in volume. Can I get any advantage by shifting one way or the other? Well, you have 1 mole of N2O4 compared to 2 moles of NO2s. So I got 2 molecules versus 1 molecule. Well, what takes up less space? Less molecules. So by shifting to the left, in this particular case, I can relieve the stress. Okay? Why? Because I'm shifting to a smaller number of moles of gas. Okay? I'm shifting to a smaller number of moles of gas. Shift to the smaller number of molecules to pack more efficiently and relieve the increase in pressure due to that piston coming down. I have less volume, so I'm going to now take advantage of that by going to the smaller number of moles of gas. Basically, the reactants require less volume, that is, fewer moles of gaseous reactants. And by decreasing the volume of the reaction vessel by increasing the pressure, the reaction would shift the equilibrium to the left toward the reactants in this example, until an equilibrium is reestablished. Literally squeezing the reaction when we increase in the pressure will cause a shift in equilibrium toward the fewer number of moles of gas. So if I increase pressure, which is basically a decrease in volume, okay, it's going to shift to the smaller number of moles of gas to reach that equilibrium again. Notice that there's a linear relationship between volume and number of moles of gas. Okay, you decrease in volume, decrease in number of moles of gas. And there's a inversely proportional between pressure. Pressure is increasing, number of moles is decreasing. So inversely proportional between pressure and number of moles of gas. Reducing the pressure, meaning the opposite effect now, is occurred by increasing the volume, which will have the opposite effect. So in other words, we're saying if I reduce the pressure, my volume will increase, and now we're going to increase into the larger number of moles of gas. So decrease in pressure, the increase in volume is a shift toward larger number of moles of gas. Remember, liquids and solids are not incompressible, so they're not part of that expression. Increase in pressure, meaning a decrease in volume, will shift to the smaller number of moles of gas. So it's important to realize these two statements are important to you. Something you need to understand to be able to make decisions when we're dealing with pressure to decide which way something's going to shift. So very important information to know. In an event that the number of moles of gaseous product equals the number of moles of gaseous reactants, meaning the same number of moles on both sides, the vessel volume pressure will have no effect on the position of equilibrium. There's no advantage shifting one way or the other, therefore it will have no effect on the shift. Let's look at some examples. Sulfur dioxide plus half oxygen gives me sulfur trioxide, and I'm going to talk about increase in pressure. So we said if we increase in pressure, then we're talking about a decrease in volume, which also means I'm looking for a decrease in the number of moles of gas. Okay, so which way would I get an advantage looking at this equilibrium? Well, I got 1.5 moles of gas on my reactant side and 1 mole of gas on my product side. Well, since I'm increasing pressure, it's going to shift to the smaller number of moles of gas, which means it's going to shift to the right. Shift to the right towards smaller moles of gas. Now, it's not going to shift forever. It's going to shift until equilibrium is reestablished. Let's look at the next one. Nitrogen gives me plus hydrogen gives me ammonia. Okay, we're going to talk about a decrease in pressure, which means I'm talking about an increase in volume, or an increase in the number of moles of gas. Okay, in this case, I got 4 moles of gas on my reactant side, and I have 2 moles of gas on my product side. So which way is it going to shift? It's going to shift toward the left. Okay, so it's going to shift toward the left, toward that larger number of moles of gas, until it reaches equilibrium again. Okay, decreased pressure. Well, that's the same thing as saying an increase in volume. Same thing as saying an increase in volume, okay, which is an increase into the number of moles of gas. Well, how many moles of gas do I have on my reactant side? Well, 1 nitrogen and 1 oxygen, that's 2 moles of gas. How many moles of gas do I have on the product side? Well, I got 2 moles of gas on the product side. Therefore, it's the same number on both sides. There's no advantage shifting one way or the other. Therefore, there'd be no shift, no change in shift. It's not going to cause it to go one way or the other. Let's look at the last one. Talking about an increase in pressure, which means a decrease in volume or a decrease in the number of moles of gas. Okay. How many moles of gas do I have on the reactant side? Well, you got 1 carbon solid and 1 water gas. Well, carbon solid's not a gas, so that's not accounted for, so you only got 1 mole of gas. Okay. On the product side, you got 1 CO and 1 H2. Both of those are gases, so you got 2 moles of gas. So according to this, we're saying we're increasing pressure, so we're going to shift toward the smaller number of moles of gas, which means in this case it will shift to the left. Shift to the left toward the smaller number of moles of gas. All right, let's talk about temperature. Temperature has a significant effect on most reactions. Okay. Reaction rates generally increase with an increase in temperature. Remember, we talked about this. I'm adding heat. I'm putting energy into the system. So I'm having more molecules moving around, more chance I can overcome that activation energy, and therefore speed up the reaction. So basically, increasing temperature will allow us to establish equilibrium sooner. But you got to remember, when we talked about Ks, we said that all those Ks are temperature dependent, meaning that there's a particular K at a particular temperature. So if I change the temperature, then I'm changing the K. So it's not the same as if we add and removing products and reactants, okay, or changing pressure, where they're going to shift one way or the other, and we're going to have different concentrations, different pressures, but the ratio is still equal to that K at that temperature. If I change temperature, that K value is going to change as well. So when you add or remove reactants or products or change pressure, the result is that the system establishes new concentrations of all the species, but the ratio is still equal to that same K at that temperature. However, for temperature changes, the numeric value of the equilibrium constant Kc varies with temperature. Therefore, it's going to change. Remember, K is temperature dependent. So if I change the temperature, my K value will change. So how are we going to determine how it's going to change, meaning increase or decrease? Well, we're going to look at heat as it's a physical entity, okay? So we're going to look in terms of an exothermic reaction and endothermic reaction and say, where's heat in terms of reactants and products? If it's an exothermic reaction, then we're talking about a release of heat. Well, that means it's releasing it as a product. So I can look in terms of an exothermic reaction as heat as a product. Okay. Endothermic, that's a case where we absorb heat. So in essence, it's basically it's taking it on as a reactant. So in essence, when I talk about exothermic reaction, I can treat heat as it's a product. And if I talk about an endothermic reaction, I can treat heat as it's a reactant. Okay, and use the same philosophy we did with Le Chatelier's principle when we talked about adding and removing reactants and products to decide which way things are going to shift. If I'm talking about an exothermic reaction and I have a system at equilibrium and I add heat to it, that's like adding more products to it, it's going to shift to the left. So if I increase heat, it's going to shift to the left to relieve that stress. Okay, same philosophy as if I said I was going to add more C or D. If it's an endothermic reaction and I add heat, I can use the same philosophy. It's like adding more A and B. Okay, well, if I add heat to an endothermic, I'm going to have to relieve that heat. So it's going to end up shifting to the right to relieve that stress. Okay, I can do the same thing with removing heat. If I remove heat, that's like pulling off my product. So that it's going to end up shifting to the right to produce more heat. In the exothermic. In the endothermic, if I remove heat, it's like pulling off some of my reactants, so it's going to shift to the left to produce more heat to make the reaction get back to equilibrium. So we use the same philosophy we did with adding and removing reactants and products and treating heat as a product for exothermic and heat as a reactant for endothermic. We see that increase in the temperature is related to adding more product in the case of exothermic reaction or adding more reactant in the case of an endothermic reaction. Ultimately, it has the same effect as if heat was a physical entity. That's what we're treating it as we're making our decisions. So, let's look at an exothermic reaction. I have reactants going to products, and since it's exothermic, delta H negative, we're saying that heat is a product. Now, if I was to increase the temperature in this reaction, now I'm not at equilibrium anymore. I'm going to have to shift one way to relieve that stress. So it's going to want to consume up that heat and produce more reactants. So it's going to shift to the left. Okay, so it will shift to the left if it's an exothermic reaction. So increase in temperature would be like adding more products, causing equilibrium to shift to the left. Now the question is, what happens to my K? Remember, K is equal to products over reactants. And we're not actually changing, this products over reactants, and heat is not part of that expression, so heat's not going to change the K. But since I'm shifting to the left, okay, something's going to happen to my products and reactants. So if I'm shifting to the left, then that means I'm consuming up my products. So what's happening to that value? It's going down. What's happening to my concentration of my reactants? Well, it's producing more, so that's increasing. So mathematically, what happens then if my products are getting smaller and my reactants are getting larger, then my K is getting smaller. Okay, so since heat does not appear in equilibrium constant expression, this would change the result, and what we get is a smaller numeric value for K. Okay, so basically if I have an exothermic reaction, and I increase heat, it's going to shift to the left. By shifting to the left, it causes my products to decrease in concentration and my reactants to increase in concentration, which then allows my whole K to decrease. Now you can either memorize this, if I exothermic, I increase heat, K will go down, or you can figure it out. I recommend figuring it out each time. It's a lot easier to understand something and figure it out than it is to memorize. We tend to forget things when we memorize them. Let's look at endothermic. We said if it's an endothermic reaction, we can treat heat as it's a reactant. Okay, so the question is, if I increase heat, which way is this going to shift? It's like adding more reactants, so it's going to consume it. So it's going to consume the reactants and produce more products, which means it's going to shift to the right. So increase in temperature will be an analysis to add more reactants, causing the equilibrium to shift to the right. Well, what happens to K now? Have products over reactants. If I'm shifting to the right, my concentration of my products is increasing, and my concentration of my reactants is decreasing. So overall, what effect would that have? Well, my numerator is increasing, so therefore my K will increase. Okay. This change results in more products at equilibrium and a larger numeric value for K. So in summary here, we're saying if I add temperature to an exothermic reaction, my K will get smaller. If I add temperature to an endothermic reaction, my K will get larger. Now, what happens if I do the opposite? What if I remove heat? Okay. Well, the opposite effect will naturally happen. Okay. If I remove heat, let's take this one, for example, my endothermic. If I go back and I remove heat, okay, well, that's like pulling it off. Well, which way is my equilibrium going to go? It's going to have to shift to the left to produce more heat since I'm pulling it off. If you look at your K, which is products over reactants, if it's shifting to the left, then my products will be going down and my reactants will be going up. Well, then my K will be going smaller. Okay, so the opposite effect is happening. In summary, for an endothermic reaction, meaning the delta H positive, the amounts of products are increased, meaning shifting to the right, at equilibrium by an increase in temperature. Therefore, Kc is larger at higher temperatures. For an exothermic reaction, delta H being negative, the amounts of reactants are increased, meaning shifting to the left, at equilibrium by an increase in temperature. Therefore, Kc is smaller at higher temperatures. And then realize the opposite occurs when you lower the temperature. If I'm pulling off heat, the opposite effect is going to happen with your K. Kc will get smaller for endothermic, and Kc will get larger for an exothermic reaction. A catalyst, you may recall, we discussed this in the previous chapter. That's a substance that increases the rate of reaction but is not consumed by it. So if I add a catalyst to a reaction, it's going to speed it up and it's going to go faster. But the question is, does it affect equilibrium? Can adding a catalyst affect equilibrium? Well, no, it's only going to make you get there faster. So if I'm already at equilibrium, all it's going to do is make my forward rate and my reverse rate go faster, but it's still going to be the same rate. Okay? If I'm already going to the left, then it's just going to go to the left faster and reach equilibrium quicker. Okay? But it's not going to cause it to shift one way or the other. It's important to understand that a catalyst has no effect on the equilibrium composition of the reaction mixture. A catalyst merely speeds up the attainment of equilibrium, but does not cause it to shift one way or the other. Just get in that direction. Just get to the direction it was going faster. So if it was going to the left, it would just go to the left faster and reach equilibrium faster. If it was going to the right, it would go to the right faster and reach equilibrium faster. Let's look at a question. I have I2, okay, iodine going to 2I, okay, with the delta H of 151 kilojoules. Suppose the system's at equilibrium at 1000 degrees C. In which direction will the reaction occur if I do one of the following things? Let's look at iodine atoms, adding them first. Okay, iodine atoms are those on the product side. So I'm adding product. Okay, so if I'm at equilibrium and I add some products, somehow it's going to have to consume up that product to be able to get back to equilibrium. So if I'm adding product, okay, it's going to have to consume up that product and make more of the reactant. We said if we add something, then it's going to shift to the opposite side, which means this can end up having to do what? Shift to the left. Okay, it's going to shift to the left until it reestablishes equilibrium. Okay, the system is compressed. What's a system at compressed mean? Well, that means that we're talking about an increase in pressure, okay, which means that I'm talking about a decrease in volume, which means I'm shifting toward smaller number of moles of gas. Okay, how many moles of gas do I have? Well, I got 1 mole of gas on my reactant side and 2 moles of gas on my product side. Well, then it's going to shift to the small number of moles of gas. It's going to end up shifting to the left. Okay, it's going to shift to the left toward the small number of moles of gas until it reaches equilibrium again. And then it will go back to its exchange. The temperature is increased. Let's see. Okay, well, if I want to talk about temperature, then I need to know if it's an exothermic or endothermic reaction. Did this problem tell me that? Not directly. But it did give me delta H is equal to 151 kilojoules, which is a positive value. Since it's a positive 151, that means that I'm talking about an endothermic reaction. We said if it's an endothermic reaction, where is heat really? We can treat it as a reactant or a product. Well, we said it's absorbing heat, so therefore it is like it's a reactant. Okay? Well, if it's a reactant and I increase the temperature, so if I increase that heat, okay, I'm at equilibrium and now I'm adding heat, so that's like adding more reactant. It's going to want to consume up that heat, okay, and produce more products, so it's going to end up shifting to the right. So endothermic reaction, therefore, is similar to adding reactants, and the reaction will shift to the right until we reach equilibrium again. Well, since heat is changing, we want to know what is the effect of that change in heat on the K value. We said, okay, we can just look at the K and see what's happening to our products and reactants to decide which way it's going to shift. Well, if I'm shifting to the right, that means I'm producing more product, okay? So that's increasing. And we consuming up that reacting, so that's decreasing. Well, mathematically, if my products are increasing and my reactants are decreasing, then my whole K has to be increasing. As I said, you can either memorize it or figure it out. So producing more products, we're shifting to the right, therefore I have less reactants, therefore we're going to have a larger K. Add in the catalyst. Well, I'm at equilibrium, so it's just going to make the forward rate equal to the forward rate and the reverse rate go faster, but it's still going to be equal. It's not going to make it go one way or the other, so adding the catalyst has no effect. Okay. Now, if the reaction was going one direction, say to the left, it would just go to the left faster and reach equilibrium faster. But that's not the case in this problem. Homework 23 has questions dealing with Le Chatelier's principle. As I said, make sure you understand the concept of Le Chatelier's principle and realize you have to use some knowledge on chemistry to decide which way things are shifting. Okay. Some things may be reacting. You may be complexing things out, okay, maybe escaping as a gas. So you got to read the problem and think about it to decide which way it's going to shift.